Okay, so substitution and elimination, and there's for linear systems, you can use either method for any problem and you will end up with the right answer in the end. However, it's often easier to use one or the other. So for example, if I have 2x minus 3y equals 2 and x plus 4y equals 12. So here's a system. So elimination is adding the two equations together to eliminate one of the variables. And so sometimes, right, like this one, you have to do a little work to make sure when you add them together, the variables are eliminated. It's probably easiest to multiply the bottom equation by -2, right? And then you can add these together to eliminate the variables. But you can also use substitution for this kind of problem. It's a little bit of kind of 6 of one, 1/2 dozen of the other, right? Kind of the same amount of work either way. But it's a different kind of technique. Substitution here, I need to solve one of the equations for one of the variables. And so my guess is that that's maybe where your question is coming from. Like if it's not written as x equals or y equals, then I have to create that. So I would move this 4y over, sorry, and that'd be now plus 12. And I chose that because that to me was the easiest one to solve for, right? And I always want to really choose the easiest option here. And so then with substitution, I would replace, right, the x in the other equation with that expression. That's 2 times minus 4y plus 12 minus 3y equals 2. And now I work through my equation here. Subtract the 24, I get minus 22. And I get y equals 2. Remember, that's only half the problem, right? I need to go back and figure out what x is. It's one of the nicer things about substitution is that you have a very easy substitution at the end. It's set up to figure out what x is. Right, so my solution then is 4, 2. Now, with linear systems, that's what this is. You can use any method. Either of those methods is going to get you the correct answer. When you have a nonlinear system, then we have to be a little more creative sometimes with a nonlinear system. So if there's an x squared or a y squared or something like that in the problem, and it turns out that elimination is much harder to do with a nonlinear system. It's certainly still possible, but we prefer substitution typically. So use substitution for nonlinear systems and use elimination for larger linear systems. So 3 or 4 variables, we really prefer elimination in that case. Okay, so the two systems are actually kind of related underneath, so you're not going to go wrong if you choose one or the other, but it could make your life harder if you choose the sort of other one. Did that answer the question?
Yeah.
Okay.
Could you do an example with an x squared and an x in the same equation?
Sure, like in one of the equations having an x squared and an x.
Yeah.
Yeah. Okay. Let me make up one here, and hopefully I'll make it so it works. It's going to be easiest for me to make it up like this. So y equals x squared minus 2x plus 3, and y equals 2x it works, I think. Yeah. Okay. I hope this works. So like this.
Yes.
So, okay. So this one is a nonlinear system, and the problem I can run into is if I just try and like, you might see, oh, if I just add these together, the x's are going to cancel, which is true, but then I'll get y's and x squareds, and so it doesn't really do what I want it to do with elimination. And so that's really the reason we kind of prefer substitution, because substitution will sort of replace all of the x's or all of the y's rather than just maybe canceling the linear terms or the quadratic terms and leaving the other term there, right? So, and again, you can try elimination with the y's, and that's going to work here, but this is a good candidate for substitution too. Again, they're very similar. It's really just a matter of perspective on this one. But what I would encourage you to think about when you're doing these problems is, you know, when you look at this problem up here, these are two lines, right? Now I didn't figure out what the lines looked like or what they were when I graphed them, right? But two lines, put that in the right spot, right? But two lines often, not always, right, but often just cross at a single point. So that point is this solution that we're finding, right, when we do the algebra. When we have nonlinear systems like this, I certainly find it helpful to visualize what the graphs look like when I can. Sometimes they're too complicated and I don't quite know what they look like, but I do know what this one looks like, right? Y equals x squared minus 2x plus 3. When x equals 0, y equals 3, and it's a parabola that opens up. Now, I don't know exactly where we could figure out the vertex. You know, but which I guess, you know, can be useful. Sometimes that can be maybe more work. But this is a parabola, and the second equation is a line. And it certainly those can intersect in a lot of different ways, right? They could cross at just one point, sort of skim the graph, or no points, or 2 points. This isn't going to tell me what those solutions are, right? Like the graph, my graph is not accurate enough, and even if I had a really accurate graph, it is likely it wouldn't tell me what the solutions actually are. But it gives me a sense of what I'm looking for. So to me, now I know, okay, I'm probably looking for two solutions here. And that's important, because if you know what you're looking for, you're going to have a better chance of finding it. Now, the way this is set up, this is kind of perfect for substitution. And, you know, what I was doing when I was, you know, scratching my head about coming up with the example is I was thinking about how it might factor when I put these together. And I just wanted one that would factor because it's going to give us nicer solutions, right, than what would happen the other way. Now, these are not the solutions. I need to make sure that these points are also on my, I need the point, so I need the X and the Y. In this case, these are both functions. So if I give you an X, that's only going to create one Y for both of these. So it's no issue in terms of which equation I put it into. So certainly the bottom one is easiest, right? Y equals 2 times 1. And when X equals 3 equals 2 times 3, which is 6. Be careful because they're pairs, so they need to go together, right? I can't just write X equals 3, X equals 1, Y equals 2, Y equals 6. That's not really what the solution is, right? It should be ordered pairs. This is perfectly fine. Or right, the ordered pairs, but don't just list the X's and Y's independently. They go together to make a solution, right? And those values are kind of roughly in line with what I would have expected from my rough sketch. Sometimes there's an issue if your graph is like a circle and a line, right? And you find this X value. If you plug this X value into the circle equation, well, you'd get 2 answers out of that, and those are not both solutions, right? The only solution is the one on the line. So when you run into that situation, it's best to plug your solutions into the simpler of the equations, right? That's the one that's kind of least likely to have this sort of non-function issue, right? So be a little careful with that. And again, having the graph, comparing my solutions to the graph is an important step, right? It helps me feel like I understand what my solutions are. Questions on this one? Yeah, the Y values, the 2 and the 6, come from plugging it into this equation, right? Once I have the X, I plug the X in, those give me the corresponding Y values. Other questions about this one? It's a nonlinear one.
So why is the point 1, 2 instead of like 1, 6 and 3, 2?
Well, because it goes with the X, right? When I take this X equals 1 and plug it in there, I get the Y is 2 times 1. So
Oh,
2.
okay.
So that this Y value comes from plugging the X in.
Okay.
And this Y value comes from plugging the other X in. Other questions? Those are like exactly the kind of questions we need, right? Because it's like, well, where does that come from? Well, you got to know that, right? Or else you're going to run into those same troubles, right? So as always, right, the questions you ask are critical to making us, figuring out what's going on. Okay, yes, I've gotten several questions from 6.3 number 7. So let's take a look at that one, not hold anyone in suspense any longer. Now 6.3 is where we have some larger systems, so 3 variables, and yes, number 7 is 4 variables, right? So the goal here, the strategy is not to solve them all at once, but to to take some time, because it does take time, and reduce it down to a smaller problem. So when you have 3 variables and 3 equations, we want to reduce that down to 2 variables and 2 equations. And though that problem then is like the first example we did, right? That's one we can solve kind of directly. And so it's the same idea here. Let's take a look at this one. And you just gotta kind of commit to it, right? And say, okay, well, this is what it is. I'm gonna take some time and figure it out. X plus y plus z plus w equals 18. 2x plus 3y minus w equals 0. Minus 3x plus 4y plus z plus 2w equals 12. X plus 2y minus z plus w equals 0. Okay. So we got to stay focused on our goal. My goal is to eliminate one of the variables. And when I look at this, some of the variables are easier than others. To me, the easiest is the z's. One reason is I already have an equation that has no z's in it, right? So this equation has just x, y, and w. And that's great. So I want to do that 2 more times so that I get 3 equations that have just these same 3 unknowns, x, y, and w. And so I can see there's another easy way to do that, which is to add these 2 together. When I add these 2 together, I get minus 2x plus 6y. The z's cancel again. Plus 3w equals 12. Excuse me. So I've got to do it one more time. I got to find another pair that when I add together eliminate the z's. The bottom one and the top one are certainly the easiest. X plus x, 2x plus 3y. The z's cancel, plus 2w equals 18. So what I've done here is I've taken 4 equations and 4 unknowns and reduced it down to 3 equations and 3 unknowns. I still have a bit of work to do here, right? But this is the step that I want. So the next step is to do that again and reduce it to 2 unknowns and 2 equations. And you've got to make sure when you do this that you eliminate the same variable each time. It does me no good to say eliminate the z's here and then add these 2 together because I can eliminate the w's. That's not moving in the right direction because I'm just eliminating random variables and I'm going to end up with equations that still include x, y, z, and w in all sorts of different ways. So I've got to make sure that whatever variable I choose, I get rid of that one each time. So here, when I look at this one, the x's are certainly the easiest to get rid of, right? Because I don't have to change them at all. I just have to add these 2 together, the top 2, and then add the bottom 2 together. Okay. Now, it's homework problem, so I'll let you guys kind of do the rest to keep track of this. But that's going to give me an equation with just y's and w's, 2 equations, 2 unknowns. And there we should feel confident about solving it. Once you get your answers, you got to just keep subbing them back, kind of work your way all the way back till you finally put in x, y, and w and figure out z, right? So you'll find x or y or w, plug that in, keep laddering your way back. So these problems are hard because they take so many steps. Each step is very easy, right? You're just adding 2 equations together, but it's hard, number one, because it's very easy to make a tiny mistake, right? You make any little addition, subtraction, miss a sign, the whole problem is lost, right? The other challenge with them is just understanding what you're trying to do, right? People know how to add the equations together, but I will see students that just sort of add them together with no intent, right? They're not really trying to get rid of a particular variable. They're just adding equations together, maybe hoping that something magical happens, right? We need to have some intent here. And that's, I think, the new thing that takes a little time to see, right? And some examples. And the intent when you have a bigger system is just to get it smaller and smaller and smaller until it's finally at a spot that you can solve it. No one really loves 4 equations and 4 unknowns. Not myself, not anybody, but I can do it. Right. And to be honest, once I know how to do that, I can do it with 6. It might take me an hour. Right. But I can do it. And that's an important step, right? Is to say, this method that I have scales. It works for small problems and it works for big problems. It's hard to do. I'm not going to ask you to do, 4 variables on the test. But by seeing that, hopefully you understand the 3 variables better and see how this process can work for lots of different things. Does that feel like you're moving in the right direction on that one? I know you may have slightly different numbers, right, if you're doing it, but you should, I think the part here actually is kind of the same for everybody. So that process is actually the same. I mean, eventually you get 2 equations and 2 unknowns. And from there, we do what we did in the first problem, which is eliminate one of the variables. Right? Once you get it down to 2 equations and 2 unknowns, you just solve it like we solved this one. Right? You get your 2 variables, your 2 solutions. You take those 2 solutions and you plug them into any one of these equations. And that'll tell you your 3rd solution. Once you have the 3 solutions, you plug those into any one of these equations, and that'll spit out your 4th solution, your final value. So usually we sort of think once you get to 2 variables and 2 equations, you can kind of treat it just like the older problems. You don't just solve it at that point. Okay. Let me take a look here. Yeah, so for what's covered on the final, just there was a question about that. What's covered on the final is listed on that final information sheet. So there's a little bit of material from the first part, but most of it is sections 4 through 6. So you can look at those, the list of topics there and read through that. So 6.3, number 6. Yeah, so sometimes you do your work, but you end up with what's called a dependent system. So I'm just going to give you a kind of simple. And so like here's a system. So the problem is there's 3 variables, but there's only 2 equations. And what we want to do here is eliminate a variable. Again, the problem is because we only have 2 equations, we don't actually have enough information to lock in on a single point. I can add the 2 equations together to get rid of the y's, but I still have a line, x plus y equals 5. So there's lots of possible solutions out there. Sorry, I wrote a y here. That's an error. That's a z. Right, the y's canceled. So this is called dependent. And what they ask you to do is they want you to express your solution, which is this ordered triple, x, y, z. They want you to express it, they say, in terms of the parameter a. And all that means is x, y, and z are like variables for us. A we think of as like a fixed value. So x, y, and z are sort of a whole range of things. A is like a fixed value. I don't know what it is either, but I sort of lock it in. And when you have a dependent system like that, for each sort of locked in value of one of these variables, the other variables are then determined from that. And so the strategy, what you do here is you just let z equal a. I'm just rewriting everything then in terms of a. So if z equals a, we have x plus a equals 5. So x has to equal 5 minus a. So you can pick any value you want for a. If you let z equal that value, x equal 5 minus a, and let's see what y is. I'm going to plug in 5 minus a for x and a for y. I picked not a great example here. It's okay. A lot of times when you do this, you'll get, my example is a little too simple. A lot of times when you do this, you will get a value of y that involves a as well, but it doesn't have to. And in this case, it doesn't. The a's end up canceling. And I get that y equals 1. So if you let y equal 1, then and x equal 5 minus a and z equal a, any ordered pair like that is going to be a solution to this system. So, and that's what a dependent system looks like. Okay. Those 3 variable systems, you got to kind of sit down and use up some paper to solve those, right? Give yourself some space to work, Don't be afraid of writing things, rewriting kind of the whole problem at certain points just to get yourself a clean start, and be very careful with your little operations, right? The adding and subtracting. It's very frustrating when you add 2 and 3 and get 6 and then your answer's wrong, right? Because it's not really about what you knew, it's just that you weren't paying attention or made a little error, and we really want to avoid those for these problems especially. So the topics here from chapter 6 are just those basic linear equations, the nonlinear systems where we have like an x squared or parabola or maybe a circle, and then the larger systems, so 3 variables. I won't give you a 4 variable one on the test, but 3 variables and 3 equations are possible. And I will tell you that if I'm going to give you a 3 variable equation on the test, I will make sure that the answers are nice whole numbers. Maybe it could be positive or negative, but I'm not going to give you one that has an answer like 23/5. That's just cruel, I think, to do something like that, right? There's no need for that with those larger systems. Now, if it's a 2 variable one, all bets are off. A fraction's not too hard to work with those. I'm confident that you can do it. But the larger systems, I won't. And well, yeah, Chris, I mean, it's a very small bit of kindness, but you're welcome. It's at least a little bit of a check, right? So if you're working through the problem and you start to get some gnarly fractions, you can then say, I must have done something wrong. And when you do something wrong in these problems, it's really best to just scratch it out and start fresh. It's very hard, even for myself, to go back into the problem and try and figure out where I made an error. It's possible, but it's really hard when it's your own work. So I recommend people just scratch it out, start fresh on a new sheet of paper and give it another shot. It's fine to leave that work. You don't have to erase all the work, but just, if you've made an error, it's hard to go back and find it just because there's so many little operations. Okay. Other questions?
I have one about find the points above the equation with the points. The number 8, section 6, homework 3, 6.3.
Oh yeah, yeah. So it gives you like it gives you a parabola like this. And they want you to figure out what A, B, and C are so that the parabola goes through a couple points. And they typically, I think they give you 3 points, right? So say -1, 0. I don't know. Let's make this let's make that +2 and then 5. I think that's going to give me a nicer solution if we work through it. But all this is it's just like a way of creating, it's a way of seeing a system kind of solving a particular problem, right? Like we have these 3 points and I want a parabola that goes through the 3 points. How do I find that? Well, one way is to set it up as a system. So each point is an X and a Y. So if I put the Y value in, and then I put the X value in, what I get then is A minus B plus C. I get like one equation. And so I would do the same thing then for each of those other points, and that would give me a series, right, of 3 equations. And then those 3 equations I would solve as a system. Okay. So you plug the x and the y in and then see what equation you get, which involves typically a, b, and c.
So for the next one, I need to put a2 a square plus b2 plus c.
Yep, equals -2. Right, because that's the y value.
Okay, I got it. Thank you.
Yep, so that'll generate those 3 equations, and then it'll look just like the other kind of systems.
Okay.
And systems really are a pretty powerful tool for solving problems. There's a lot of situations where we have a number of things that are unknown, but we know some relationships between those different things. And putting all that information together is really a system, right? And so this is a very much there's a lot of real world problems that are solved by looking and thinking about systems. So there's a couple pseudo real world problems here on the homework, not too many, but it's a field of math called linear algebra. Is working with these kinds of systems and understanding their solutions. Other questions? Anything else?
Yes, I could. I have a question on section 6, homework 2, 9.2.
Homework 2, yeah. Which problem?
Like question 9.
Yeah, so that's like a little application problem.
Yeah.
So they say 2 cheeseburgers and a small order of French fries is 780 calories. So it's 2 cheeseburgers and 1 order of French fries. And then 3 cheeseburgers and 2 orders of French fries should equal 1360. Okay. So for this one, right, the things we don't know are the calories in the cheeseburgers and the calories in the French fries, but we know these kind of 2 combinations of them. These are linear combinations. So it generates a linear system. Okay. So this one now, we've sort of taken it out of the application problem and turned it into a pure math equation system. So we can solve that system by either elimination or substitution, right? And then find the values of F and C. Does that help?
So I didn't really. Okay, now my question is, let me see. Okay, which means we just kind of like so how can I put it? Put in the set in the figures in the can I put this statement now?
I mean, if I were to solve this one, I typically prefer elimination. Unless I have a nonlinear system, I almost always use elimination. So I would focus on eliminating, right, this variable F.
Okay.
To me, that's the easiest, because if I just multiplied this top equation by -2, then when I add those together, the -2F and the 2F would cancel.
Oh, okay.
But I've got to, multiply all those pieces by -2.
Like -2 then, yeah.
Mm-hmm. Then when I add them together, I'll get an equation with C equals some number
Yeah.
and,
Okay.
and be able to solve that for C.
Yeah, that's better now.
Okay.
Thank you.
Yeah, of course.